I was just telling everyone, you don't have to wait till the end to ask questions. Just yell out a question. So what I want to do now is, as I said, I'm just going to take some selected topics that I've talked about already, and I want to dig into them a little bit more in the combustion theory side. And what I'm going to talk about next is flashback and flame holding. Now, flashback is probably something, if you've taken combustion, if you've looked in Steve Turn's book or Professor Law's book or Glassman's book, they talk about flashback. What is it? It's the upstream propagation of a premixed flame. And the reason we don't like it is because it's usually into a region not designed for the flame to exist. Flashback is one of the key mechanisms for major, massive part failures in gas turbines. And so it occurs when the laminar and or the turbulent flame speed exceeds the low flow velocity. So the quote, the fish can swim upstream. The flame can swim against the stream and propagate upstream. An important point I want to emphasize, though, is in reality, nobody who makes a gas turbine worries about flashback. All right? It's this interesting academic concept, but nobody ever worries about flashback. What people who make gas turbines worry about is something which I'm going to call flame holding. This word flame holding is sometimes used to mean flame stabilization. If you look at people who make gas turbines, use this word flame holding to mean something very specific. And what they do is they will take a premixing nozzle and they will have a torch inside the nozzle itself. And somebody will say, go, and they'll light the hydrogen torch. They'll introduce a flame into the nozzle, and they'll shut the torch off. And the question is, does the flame go shooting outstream, or does the nozzle hold a flame? Okay, that is the real test. Because if a nozzle is resistant to flashback for the most part, but there's always hiccups, right? I've been talking about grid transients and all this crazy stuff. What if somehow, for some crazy reason, or there's a condensed droplet of propane that goes blasting through, somehow a flame can get introduced into the nozzle, and the flame can't spit it back out? That's the issue. So flame holding is it's a more severe and rigorous test of the nozzle. And as I'm going to talk about, what makes it is the problem has there's hysteresis. So a nozzle that can very happily sit with the flame parked outside of the nozzle in the combustor, the flame will not flash back. It will never flash back. If somehow something hiccups, the system, something crazy happens, there's an oscillation. If the flame can come back and stay there, and it doesn't just go shooting back out when you go back to your normal operating condition, that's bad. And it turns out that this is much, much more harder to do because of these hysteretic elements that I'm going to talk about. For example, wall temperature effects. Once the flame comes back, it starts to heat up combustor walls, and those walls can stabilize the flame, whereas when the walls are cold, you can't. That's one example. Another one is the effect of boundary layer and swirl flow stability. And this is really a fluid mechanic problem, is that it turns out that flames propagating in boundary layers like to make boundary layers separate. Flames in swirl flows, and I'll talk about swirl flows a little bit because I'll assume that people are less familiar with those. Swirl flows actually have these interesting hydrodynamic stabilities which also have hysteretic elements, and the flame can kick you from one side to the other of the two branches of your solution. And so again, this flame holding is a much more severe criterion. And it's interesting because there's not much about it in textbooks. And I'm going to try to give you a little bit of feeling for why there's these hysteresis elements and why flame holding is a more severe test than flashback. So let's talk a little bit about mechanisms. So I've talked about flashback and flame holding, but there's different ways or different mechanisms by which a flame can flash back, and different ways or mechanisms by which a flame can hang on once it's back there. First one is flashback in the boundary layer. This I think is probably obvious, is that the boundary layer has a low flow velocity region, and that's going to be where a flame is going to want to shoot upstream. So actually I have a very nice, I put show video to remind myself to show the video. See, they're not linked. And this is where the flame and this is a flame shooting up the boundary layer. You see it, actually, if we look on this side, this is a me scattering image, so that what you're looking at are PIV seed particles, and you see when the PIV seed particles go through the flame, these must be combustible seed particles because they go away. So let's just it's looping right now. Let's just look at it. So here that flame it's shooting upstream in the boundary layer. What you're seeing over here, this is CH chemiluminescence. So the region that's basically, there you go. So here's the flame. It's shooting upstream. There you see the chemiluminescence, the light emissions telling you that you got combustion going on in this region. And notice the shape of this flame. You can see it's penetrating farthest some distance from the combustor walls. This is the combustor walls. But this would be an example of flashback in the boundary layer. And I'll talk a little bit more about this later. The other example is, the other way flashback can occur is in the core flow. This would be an illustration of flashback in the core flow. What's happening here is somehow the flame is able, not even in the boundary layer, but in the main high velocity flow, the flame is able to find a way to shoot upstream. Now, if you have a well-designed system, this shouldn't happen, right? Because the flow velocity should be high everywhere. The flow velocity should be everywhere greater than the flame speed. However, and so if that's not the case, then that's flashback mechanism is kind of trivial. If you have a low velocity region, the flame can shoot up. But I want to show you that there's some actually non-trivial mechanisms whereby flames can shoot up in the core flow when you have swirl in the flow. When the flow is spinning, the flame starts to interact with the hydrodynamic stability of the flow, and it creates a mechanism. If it's just the flame or if it's just the flow, nothing can happen. But the two come together and they create additional physics, and they create a new mechanism, and the flame can shoot upstream in the core flow. Another mechanism by which you can get flashback is during combustion instabilities. Combustion instabilities, you get the flow is oscillating. You get these large amplitude flow oscillations, and the flow oscillations can in some cases lead to nearly reverse flow or much lower velocity flow in the nozzle. So you have this nozzle, let's just say the nominal flow velocity is 50 meters per second. You get a violent instability that the flow velocity might swing between 10 and 90 meters per second, 80 times a second. And during that 10 meter per second excursion, if the flame has enough time to blast upstream, that would be flashback. It turns out, in fact, that oftentimes when you have very severe combustion instabilities, the reason that they cause the most damage is because they cause flashback. Combustion instabilities cause long-term damage through fatigue, but they can cause very catastrophic damage in a matter of seconds by inducing flashback. I'm not going to talk about this mechanism here because I'm going to focus my discussion on instabilities tomorrow. So there's different ways a flame can get upstream. And as you can imagine, as I'll talk about a little bit later, the relative significance of these different mechanisms changes with your nozzle design, geometry. It changes with operating conditions like velocity. It changes with your fluid mechanic features like the amount of swirl in the flow. Okay, so let's start by talking about boundary layer flashback. How can a flame shoot upstream in the boundary layer? What I have here is a slide. This is kind of a classical treatment of boundary layer flashback. If you look in any combustion book, you'll find this treatment. I want to very quickly review it, and then I want to show you that this classical treatment really misses some really important features. And actually the key things that it misses is if you neglect the effects of heat release and you neglect the effects of stretch, you can reproduce these classical arguments. So basically the idea is this. If we zoom in on the boundary layer, let me go over here. We have, what I'm drawing here is the velocity profile. So you have some axial velocity, which I'm denoting as ux, and then there's this gradient at the wall. I'm calling it dux by dy at y equals 0. So that's what this dashed line denotes. And then what I'm drawing here is the flame. And as you all know from combustion, is that flames, there's some quenching distance. I'll call it del Q, where the flame quenches a certain distance from the wall. So the million-dollar question is, how high is the flame speed at this quenching distance relative to the flow velocity? If this flame didn't quench, if flames didn't quench at the walls, all flames would flash back because the velocity's got to go to 0. But flames quench. And so the question is the flame speed with which the flame can go this way bigger than the flow velocity there? So that's what I have here. Flashback occurs when the axial velocity at this quenching distance, when that's equal to the flame speed. And you might wonder, what's all this junk I have here? I'm pulling this straight out of my combustion textbook. And S of U means the flame speed with respect to the reactants, the unburned. D means the displacement speed rather than the consumption speed. And if you don't know what I'm talking about, don't worry about it. Just think of this as the flame speed. But I'm being precise about flame speeds because highly stretched flames have both displacement and consumption speeds, and they're different. Okay, so when the flame speed at del Q, when that's equal to the velocity, that's your critical flashback condition. So if you take the velocity and you expand it in a Taylor series about the wall condition, the axial velocity at the quenching location, ux at y equals del q, it's approximately equal to, well, the velocity is 0 at the wall, so the leading order term is 0. And so the 0th order term. So the next term is the gradient, dux by dy times del q. All right? And I'm going to call this, this is oftentimes called the velocity gradient. I'm going to call it g sub u for velocity gradient. All right? So this velocity, so what I'm going to do is I'm going to replace this velocity by g sub u times del q. And if I take that and I substitute it in here, what I get is this simple formula for the conditions under which I get flashback. Then the velocity gradient times the quenching distance divided by the flame speed is equal to 1, or of order 1, because there's some other effects. When that's of order 1, you're going to get flashback. And so what we can do is we can define a Karlovitz number as this velocity gradient times quenching distance divided by the flame speed. And we can say, well, when this critical Karlovitz number is of order 1, we're going to get flashback. Well, this basic idea is very well borne out by experiments in open flames, such as Bunsen flames. All right? So just to illustrate this, what I did was we pulled a whole bunch of very classical flashback data from the literature, from these references. And what these guys did was they calculated critical velocity gradients, GU, as a function of phi, and at different preheat temperatures. T sub u denotes the temperature of the unburned temperature, the reactant temperature. And as you might expect, for a given preheat temperature, the critical velocity gradient is highest at an equivalence ratio of 1, because the flame speed's higher. So you've got to have the highest gradient in velocity to keep the flame from flashing back. And then it falls off on both sides. So this roughly mirrors the dependence of the flame speed on fuel air ratio. All right? And as we increase preheat temperature, you can see that critical velocity gradient blasts up because the flame speed is exponentially sensitive to temperature. So as your preheat temperature goes up, you've got to have more and more of a velocity gradient. You have to have basically a higher and higher velocity core flow to keep the flame from flashing back. All right? So this is all that data in dimensional form. But now what you can do is you can go into Chemkin. You can run a detailed kinetics calculation. Let me back up one slide. I can go calculate the flame speed. And what I'm going to calculate here are unstretched laminar flame speeds for all these mixtures. And I'm going to go calculate the flame thickness. And let's just crank this thing through. And so if you run those detailed kinetics calculations, so no empiricism, nothing, and I plot that Karlovitz number, you can see that all these mixtures flash back. By the way, the dark symbols is the methane data. I'll talk about the other symbols in a minute. All these mixtures flash back basically at a Karlovitz number of about 0.5. All right? And you might say, well, why not 1? Why not 0.5? Well, it depends on your definition of flame thickness. And, there's lots of, the scaling is of order 1. You can see there might be a slightly downward trend. What I also have is I took they did the same thing for propane, and I have that same propane data here. And you can see the propane data is also, all of it collapses at these different preheat temperatures into a range of around 0.5 to 0.75. You can definitely see a slope here. And this is probably a stretch effect, all right, which I'll talk about a little bit later. OK. That's a laminar boundary layer flashback. Well, what happens if you're turbulent? OK? Well, we can take the same basic ideas, let me just back up a minute. We can take this same basic equation and we can relate these we can take these and we say, well, if the average velocity at del Q is equal to the average flame speed at del Q in a turbulent boundary layer where everything's oscillating, that should also be my flashback criterion. However, there's an important question, and that is, how accurate is this expansion for the turbulent boundary layer? And turbulent boundary layers, as you probably know, are multi-zone. There's actually two distinct regions. There's what's called the laminar sublayer, which I'll call delta sub V, and then there's the overall boundary layer thickness. So if the laminar sublayer, del V, if that's greater than the quenching distance, that basic scaling should hold. However, in reality, that's probably not generally the case. And so what you can see is here I have a turbulent boundary layer drawn in. And here's your critical velocity gradient. What I've done is, what this basic theory does is it assumes that your quenching distance lies within this region where it's approximately linear. And if the quenching distance, however, lies outside of the laminar sublayer, you might be up here. And so what you can see is that the critical velocity gradient that you would get would be quite different. If I took dux by dy at y equals 0 times del q, I would get this number, whereas in reality, if the quenching distance is here, you'd get a very different gradient. And so it turns out that most literature data shows that the critical velocity gradient in turbulent flows is about 3 times the laminar value, which tells you that that this inequality doesn't hold. But still, same basic ideas. Still the same basic idea, is just that you can't use that simple first-order Taylor series expansion to approximate what's happening. What's also interesting in turbulent flows is, as I mentioned, there's significant space-time variability. So this is some really neat data taken from Thomas Sadelmayer's group in Munich of a flashback. And what they did was they created a, quote, a steady-state flashback. And what they did was they created a diffuser with just a very slight incline. And so that flame is statistically sitting at one spot. And look at that flame swimming upstream, but you see it washes down, and you see these fingers shooting upstream. Very, very likely what's happening here, and by the way, this is a really interesting subject for future research, is the flame is interacting with these, with the hydrodynamic stability of the turbulent boundary layer. You know, the turbulent boundary layer is itself unstable. It has these Tolmien-Schlichting waves, which you might have heard of, and these lambda waves. And the flame is interacting with those, and it's changing their character in a really interesting, unsteady manner. There's lots of kinetics is a great field, but there's an enormous number of super interesting problems in combustion just related to how heat release interacts with hydrodynamic stability. It's a really understudied subject. And you can see it in these images. Really, really neat images showing you this flashback phenomenon. OK.
Was that really in the boundary layer? It seems like it was moving fastest up the core flow region, towards like the center of that.
This is a top-down view.
Oh, okay.
So what's happening is, can I draw on something? What's happening is there's a diffuser channel, and they're looking down. So if this was obviously there's going to be impurities. The approach flow velocity profile isn't perfect, but that flame should have been a straight line across if the flow was, or actually, since that wasn't clear, let me just show it one more time. Whoa, chalk, that's old school. I haven't used chalk in my whole life. That's how young a faculty member I am. I've never used chalk. So today will be the day. So this is the configuration. And so the flame sits like this, and they're looking down. OK? All right. So let's see. All right. Now I want to back up a little bit. So that's classical treatment. Works pretty well for open Bunsen flames. It doesn't work well at all for a confined flame, and I'll talk a little bit about why. And one of the key reasons it doesn't work well at all is if we back up, if we look at these two assumptions, I didn't say it explicitly, but really we totally neglected the effective heat release. And how do we neglect the effective heat release? Because what we did was we said, let's assume I know the flow velocity. I'm going to tell you what the flow velocity is. I'm going to tell you what the critical velocity gradient is. In reality, the flame interacts with the approach flow. The flame has this, there's a density jump across the flame. The flame influences the flow velocity coming at it. So it's a coupled problem. So in reality, you've got to calculate it simultaneously. The other reason is stretch. This flame is very obviously positively curved. Stretch changes the velocity. So what should this flame speed be? Well, it's a function. Again, it's part of the problem to figure out what this curvature of the flame should be. So I want to show you that. So first I want to talk about some hydrodynamic influences. And to do that, I want to back up a little bit. Now, those of you, how many of you know what the Darius Landau instability is? Ah, OK. I thought I was going to be reviewing stuff. So we'll spend a minute on the Darius Landau instability. I'm not going to prove it to you, but I'll just tell you that if you, let's think about a situation. This dashed line denotes my flame. Okay, so there's this I'm just going to treat the flame as a sheet, a discontinuity, which I can for many applications because the flame is so thin relative to my hydrodynamic scales. Here's my flame. If I have a flat flame, the problem's pretty trivial. I got flow coming at it at some flow velocity, and it accelerates through the flame. All right? Acceleration implies what happens to the pressure across the flame? has to drop, right? Because in order to accelerate a flow, it's got to have a force. That's Newton's law, right? You got to have F equals ma. The flow is accelerating, pressure's got to drop. Flames cause pressure drops, all right, static pressure drops. And because of the flow acceleration, the flow accelerates because of gas expansion, all right? Now, what happens if I don't have a flat flame, if I have a curved flame? So that's what I'm drawing here. So this is a flame that's almost flat, but it's curved. I added a little curvature to it. And I'll just, you can do the calculation. You'll have to take my word for it. But if you sit down and you say, if I have a weakly curved flame, what happens is the part of the flame that bulges out into the reactants, I guess that would be the convex part, I think. Convex, yes. The flow will decelerate, okay? So the flow feels the flame and it starts slowing down. What does that mean is happening to the pressure? The pressure is rising. The flame, although globally the flame is going to impose a pressure drop on the flow, locally the flame is imposing an adverse pressure gradient on the flow. The flow is decelerating. The flame is back, it's like a back pressure. It takes extra force to shove the flow through the flame. The pressure is rising. Okay, exact opposite thing happens on the concave part. The flow accelerates. So now there's even more of a pressure drop. The pressure is actually already dropping even before the flow hits the flame, then it drops more through the flame. All right? So what happens is if I'm following a streamline through here, what I would see is, actually I have it down here, where I'm plotting the pressure and the velocity along this line right here. Okay? So I'm plotting the pressure and velocity along this line. That's what's being plotted on the y-axis. This is dimensionless distance. K is the wave number of the disturbance. And I'm plotting it all the way up to the flame. I should have drawn it farther. In fact, I will on the board. Now that I know how to use this device on my over here. But if I were to draw the pressure, what the pressure looks like this. It rises, and then what happens at the flame? It drops like that. So net pressure drop globally, but there's an adverse pressure gradient at the flame. The exact opposite happens, and by the way, the flow velocity does the opposite. The flow velocity decelerates, then it accelerates through the flame because of the gas expansion. Okay, so that's really interesting, and it's in particular, what I'm going to be interested in are flames that look like this, because by geometric necessity, the farthest forward part of a flame has got to be positively curved. It's got to be curved into the reactants, right? Like I've drawn here. The farthest forward part of a flame's got to look like that. So I got a special interest in positively curved flames. And so what do we know? Positively curved flames impose an adverse pressure gradient. They decelerate the flow. Well, all right, now suppose this flame is in the boundary layer. Well, what do you know about boundary layers? Boundary layers don't like adverse pressure gradients, do they? What happens when a boundary layer sees an adverse pressure gradient? It can cause the boundary layer to separate, right? So flames can make your boundary layer separate. A flow which is very happy, a straight pipe where the flow is very happy, having a nice boundary layer, will actually detach, separate, and you'll have a reverse flow region. If the flow is swirling, this subject you'll have to take my word for it, because if you're not familiar with swirl flows, I'll just tell you, swirl flows have this phenomenon called, actually let me just do an aside, just so everybody is with me. As soon as you add swirl to a flow, it does all kinds of crazy things to the flow, which make life really interesting. All right, suppose I have a flow that looks like this. I got a pipe. All the flow is going left to right. And let's just say the flow is going some really high velocity, 100 meters per second. It's just shooting through there. Now let's say I add some spin, some swirl to the flow. All right? Well, no problem. It just introduces an azimuthal component to the velocity. But once the ratio of azimuthal momentum to axial momentum starts to get on the order of 1, so when the flow is spinning, going in the azimuthal direction just as much as in the axial direction, you get a phenomenon called vortex breakdown, all right, where the flow all of a sudden will do this crazy thing where it will stop. Okay, it's moving 100 meters per second. It's just blasting through the pipe, and it's like it runs into a brick wall. It stops, and you get this bubble on which time average might look something like this. And so then what happens is the flow goes around it. It looks like, it physically looks like somebody just stuck a ball into the middle of the flow. And this is called vortex breakdown. It's a natural hydrodynamic stability of swirling flows. This is why combustors like to have swirl flows, is because you can get natural flow recirculation without any type of flow, you don't have to stick metal into the flow to make flow separation. Well, it turns out that, well, what controls vortex breakdown? the amount of swirl in the flow is important. But it turns out that also vortex breakdown is a very sensitive function of the pressure gradients in the flow. If the flow is accelerating, if there's a favorable pressure gradient, it takes more swirl to make the flow break down. If there's an adverse pressure gradient, the flow breaks down easier. It's easier to break down. So what happens? Well, in a swirl flow, the adverse pressure gradient the flame imposes on that swirl flow can actually make the flow break down. All of a sudden, you have reverse flow in your nozzle, which wasn't supposed to happen. I'll talk about that a little more later. You guys know about triple flames for non-premixed flames? Does that ring any bells? If you have a fuel and air going over a splitter plate, what does the flame look like? Well, you can, if the scalar dissipation rate isn't too high, you can get what's called a triple flame, where you have a rich premixed flame here, a lean premixed flame here, a non-premixed flame here. Well, people have gone in, and so what you have is basically a stoichiometric premixed flame here. But people have gone in and they've realized that actually, the flow velocity at the leading edge of the flame is much higher than the flame speed. How can the flame sit there? And the reason is for the reasons I just talked about. You got positive curvature, so the flow is actually decelerating. Oh, I'm offset here. This shouldn't look like that. The flow is actually decelerating ahead of the flame like this because of the gas expansion. And so the flame can actually sit in a spot where the flow velocity is higher than the flame speed. The exact same reason. And then actually, the first question I had asked you about your stability, your familiarity with the Darius Landau instability, this actually causes flames to be stretch-insensitive flames to be intrinsically unstable. So you can't actually have a flat flame that just sits there. It's a nice mental construct for academics, but no real flame will just sit there without developing spontaneous wrinkles. And you can see that from this picture here, that this part of the flame has some, if the flame is stretch insensitive, so the burning velocity is independent of the curvature, because the flow velocity here is low, drops, that means this flame is going to propagate even farther out, right? Because it's got some flame speed. And that's going to cause the curvature of the leading edge to be even steeper, which is going to cause it to decelerate even more. So this bulge is going to grow. What happens here? This flow velocity is accelerating. It's greater than the flame speed. This bulge is going to grow. And so what you end up with, this Darius Landau instability, purely a fluid mechanic, hydrodynamic instability associated with the fact that you have a flame with this gas density discontinuity across it leads to this. So there's a lot of discussion in sort of most textbooks on the Darius Landau instability, but I want to emphasize that this same basic phenomenon, that a curved flame causes an adverse pressure gradient and flow deceleration, also leads to all these other interesting phenomena which control flashback and flame holding, which is what I want to emphasize now. So one other important effect which I want to emphasize here is heat conduction and influences on boundary layers. What I have here is a plot. This is again, this goes back to the point of what does the flow velocity profile look like? So what's this velocity profile look like to understand flashback? And I want to emphasize that only in the zero heat release limit, which isn't a very interesting limit for combustion, is that flow velocity, can you prescribe it? Otherwise, it's part of the problem. And so think about what happens is if you have combustion. Well, combustion causes back heat transfer along metal. It causes heat transfer to boundary layers. All right? So if you go look in Schlichting's boundary layer book, there's some problems on boundary layers with heat addition. You can, it's a fairly, I'm not going to prove it to you, but you take your boundary layer equations and you can prove that if you have heat addition in a boundary layer, it causes an inflection point in your boundary layer, just like an adverse pressure gradient does. So not only does a flame with curvature give you an adverse pressure gradient, but also the fact that you have boundary layer heating causes an adverse pressure gradient. And actually, just to illustrate this, this is some data from our lab where we took a flow, non-reacting, get a nice boundary layer profile. As soon as we turn on the flame, look what happens. You get this inflection point. The whole boundary layer gets a lot thicker. So if you were saying, well, if my quenching distance is this, my velocity should be this. But look what happens as soon as you turn on the flame. The critical velocity drops to something much lower. And so, again, this points to this hysteresis between flashback and flame holding. Once the flame can propagate upstream, start heating up metal, it has a lot easier time staying there than it would than it would otherwise. Okay, so let's dig into these heat release and stretch effects a little bit more. And I want to show you a really neat experiment that was done also by Thomas Sadelmayer's group. What they did was they compared the critical velocity gradient for two geometries. So this is just your classic Bunsen flame type geometry. And they figured out what was the velocity gradient required to make the flame flash back in this environment. Then what they did was they put just a very subtle lip on the flow to stabilize it, the flame here. And they said, well, what's the velocity gradient required to make the flame shoot upstream in this geometry? Does anybody want to take a guess what happens? So if you take this classical theory, it would predict that there is no difference between these two geometries. You got some critical velocity, you got some velocity gradient in your approach flow. Well, here is their results. Here's the critical velocity gradient as a function of fuel-air ratio. Here's the unconfined, here's the confined. There is about a factor of 5 difference, almost an order of magnitude, about a factor of 5 difference between how easy it is for a confined flame and an unconfined flame to flash back. All right? Well, and so what this points out, this goes, like I said, this is particularly important in understanding this distinction between flame holding and flashback. Once a flashback event has occurred, it's really difficult to expel the flame from the combustor. In other words, if you design the system, let's just say that you said, oh, a critical flashback, critical gradient of 0.5, that's everywhere greater than this result, I should be fine. You can see once the flame is confined, that's not good enough. The flame will stay there once it's stabilized. So what's happening here? It's entirely due to this, the effect of curvature, curved flames on the approach flow. The leading point of the advancing flashback, the advancing part of the flame, it's positively curved. And what that does is gas expansion causes the approach flow, changes the approach flow velocity. So in other words, whoops, I put stretch effects. Let me jump ahead 2 slides for a minute here. I want to present this in a little different order. So in other words, gas expansion across a curved flame, it changes your approach flow. Your approach flow isn't what it is when the flame's not there. And so what that does is the velocity in front of the flame isn't the cold flow velocity anymore. It's a different velocity. It's a lower velocity. And in extreme cases, what can happen is you can actually cause the boundary layer to separate. And then what happens? So what happens if the boundary layer separates? The approach flow is sucking the flame back into the nozzle. Your flow, which is nominally in this direction without a flame, as soon as you introduce heat release, near the walls, it's going backwards. And so actually, these are some really nice images taken by the group at Lund in Experiments in Fluids paper from 2010, showing this exact phenomenon where a flame causes boundary layer separation. So this is an image of the instantaneous flame. These are streamlines of the flow. And what I've done is I've hatched out the separated flow region. So look at that. Right in that positively curved region of the flame is causing reverse flow. It's actually causing boundary layer separation. So what happens? Well, the flow is going backwards, so the flame shoots upstream, which causes the boundary layer to separate, so the flame moves upstream. And so the flow is actually sucking the flame back up into it. You totally have to include heat release, gas expansion effects in order to understand this problem. In order to illustrate this further, what I did was I took that same data from Sadelmayer and I took the critical velocity gradient of the confined situation normalized by the unconfined situation, and I plotted it as a function of the gas expansion ratio, TB on TU. And their data looks like this, basically showing you that as you increase the expansion ratio across the flame, this deviation between the unconfined and confined results gets bigger and bigger. So again, the classical theory totally misses this point about the fact that this gas expansion effect. There's also a stretch effect. Okay, so I've talked about, let me just back up for a minute. So if you take if you neglect the effects of heat release and stretch, you impose the velocity and you know what the flame speed is. So I just told you that in reality, you don't know the velocity because it's a coupled part of the problem. Now we can talk about the burning velocity, the flame speed. That's also part of the problem. If you have a flame that's stretch sensitive with a non-zero Markstein length, that's also going to affect the problem. And in particular, what we care about is, since the leading point of the part of the flame is positively curved, we care about the sensitivity of flames to positive curvature. And in particular, if you have flames with negative Markstein lengths, what does positive curvature do? It accelerates the flame speed. So what kind of fuel, who has negative Markstein lengths? Lean hydrogen. Lean hydrogen flames have, So this goes back to this point about why hydrogen flames are hard to not flashback. Not only is the laminar unstretched flame speed high relative to methane, but they're also super duper stretch sensitive. So when they have that positive curvature, their flame speed goes up even more. Lean methane also has a negative Markstein length, and then a rich heavy fuel, like a rich propane flame would have a negative Markstein length. Okay. So in other words, so the leading point of the advancing flashback event is subject to positive curvature. So if you have a negative Markstein length, this can cause the actual flame speed at the quenching at y equals del Q to be much, much greater than the unstretched flame speed. This superscript naught denotes the unstretched flame speed. And so in other words, what this says is that the unstretched flame speed can be a very significant underestimate of the flame speed. Very important effect. Okay. So that's all I'm going to say about boundary layer flashback. Does anyone have a question? Yes, sir.
I wanted to ask, a little unclear, the difference between the confined and the unconfined, what exactly is causing more stretch? Is that
okay, so the reason is in the unconfined, you have such a massive pressure gradient, adverse pressure gradient at the outlet, that the back pressuring that the flame imposes on the boundary layer is just totally negligible to the fact that you have this massive pressure gradient, adverse pressure gradient. Here, the flow is nominally a zero pressure gradient flow, and so that negative pressure gradient the flame imposes on the flow totally changes the problem. So key point is flames cause this local back pressure. Okay, so I've talked about flames propagation in boundary layers. Now I want to talk about flames propagation in the core flow. How is it that you have a flow where the velocity is everywhere greater than the flame speed? How in the world can the flame propagate upstream of the flow? All right? And here, as I mentioned, well, this problem's kind of trivial if there's no swirl. It can't unless the local flow velocity is too low. But if you have a swirling flow, bang, that can give you a new mechanism. That's what I'm going to talk about now. In particular, what I'm going to talk about is a mechanism where I've called combustion-induced vortex breakdown. So just as I showed you in the previous slide, you can get combustion-induced boundary layer separation. You can also have flows which don't want to break down. Combustion can force vortex breakdown. All right? Okay, so actually, this was the intro that I should have given a few slides ago. But I want to first just real quickly give you a little bit of an overview on vortex breakdown. And as I mentioned, the degree of swirl in the flow, which I'll call S, has very profound influences on flow structure. And the most prominent feature, when you have high swirl flows, when the swirl number is on the order of 1, you get this vortex breakdown phenomenon, which I've drawn here. All right? So you get this natural recirculation bubble in the flow. And here's a couple nice little flow visualizations illustrating this. This is flow coming out of a jet, and what you see is you have this, if you can use your imagination, you'll see this jet flow coming out, and then you'll see the flow just naturally, it's like dividing around something. And you might ask, well, why is it dividing around this? And this is that leap forward stagnation point of the vortex breakdown bubble. So you have this recirculating flow. The flow looks kind of crazy on an instantaneous basis because you have all these hydrodynamic instabilities present. You can see this jet actually kind of gets wrapped around here due to these. You get these helical modes present in the flow. Here's some other visualizations. This is a die which is put dead on the center axis of the flow. And what's going to happen to this die? Well, if there was no vortex breakdown bubble, it'd be kind of boring. There'd be a die streak shooting all the way across. But look what happens to this die. It's scooting along, and then all of a sudden it hits the stagnation point, and then it goes whipping around the vortex breakdown bubble. So you can kind of visualize this thing in this vortex breakdown. This is another photo showing the same thing where they've slightly changed the way they're doing the die, so some of it gets entrained into the vortex breakdown bubble. So the die is zipping along, and then you can see the bubble right there. All right. I am going to, because I'm being very wordy, skip the next two slides, and where I talk about some of the unsteady features of swirling flows, which are really interesting. I just want to real quickly talk about flow stability and vortex breakdown. And in high Reynolds number flows, you have well, in swirl flows, where the Reynolds number is a parameter, you get what's called a fold catastrophe, which, for those of you who've had a dynamical systems class, you may be familiar with. And what I have here is a bifurcation diagram. And the y-axis denotes the magnitude of the maximum reverse flow velocity. This axis denotes the swirl number. This axis denotes the Reynolds number. And so at low Reynolds numbers, what you get is this nice, smooth, monotonic relationship between reverse flow velocity and swirl number, right? But what happens right at that critical Reynolds number, you get this fold that develops in the flow, all right? So what does that mean? Basically, what it means is that in this region of swirl numbers, what's happening is there's no vortex breakdown. In this range right here, you have vortex breakdown. And there's this intermediate range where you can have the same flow, the same everything, can either break down and have reverse flow, or it can all go in the same direction. Okay? So I've illustrated that same here. This is a notional plot based on some calculations from Zvi-Rusak at RPI. This is swirl number, and this is a measure of the swirl flow vortex core size. And what it shows is really high swirl numbers, you always get vortex breakdown. The flow will always be broken down. Low swirl number, no breakdown. The flow is always just moving axially. But there's this big intermediate region where either can happen. It just so happens that most gas turbines are designed for a variety of reasons that they actually sit somewhere in this hysteresis region. All right? So what does that mean? Let's think back about our a very typical design for a gas turbine combustor might look something like this, where I have this swirling premix flow here, and what happens is that this rapid expansion is a huge adverse pressure gradient, and so what that does is it'll force vortex breakdown. The flow will break down right about here, and you get this nice recirculating flow pattern, and that recirculation flow pattern stabilizes the flame. And so nominally, you'll have a flame that might sit somewhere out here like that. But the flow in the nozzle passage is actually where you get this phenomenon, if the flow in the nozzle passage is sitting in this hysteresis region, what that means is, well, the flow won't break down. It can have a non-breakdown state, but it also means if you whack the flow hard enough, you can kick it to that upper state on that top right diagram, and the flow can break down. All right, well, it's a straight pipe. There's really nothing to perturb it except for gas expansion. Suppose I could somehow introduce a flame into this nozzle section. If that can force vortex breakdown bubble, now all of a sudden you have a low velocity region. So although on average the flow velocity is much higher than flame speed, I can locally create a region where the flow velocity is below, even negative. And that's basically combustion-induced vortex breakdown in a nutshell. Again, I'm just going to jump over this because I'm talking too fast, but too slow. But I showed you some intermediate calculations, but I'm just going to jump straight to the essence of it. And by the way, Thomas Sadelmeyer at Munich has done great work on helping us better understand flashback, and this is pulled straight from his stuff. And here's the idea: I have this flame, just the picture I just drew here. And again, it's a positively curved front with gas expansion, which causes the approach flow to slow down. It imposes an adverse pressure gradient. Swirl flows don't like adverse pressure gradients. They want to break down. So what happens is the flow breaks down. So now I have reverse flow. So the flame starts moving back. As it moves back, it causes the approach flow to break down. And so that vortex breakdown bubble just marches upstream, and the flame just merrily follows it back. So basically, the flow sucks the flame back into the nozzle. So again, on average, the flow velocity is greater than the flame speed. But locally, it's not. OK, does anyone have any questions about flashback? I think the major point there you can see is there's some very interesting and new degrees of freedom when you start coupling kinetics with gas expansion with hydrodynamic flow stability. That you take any two of those, you get one thing. You add all three together, you get some new phenomena which aren't present. OK, so I've talked about flashback. Now I want to talk about flame stabilization and blow-off. So this is another one of those operability issues. And I want to talk about what controls the situations when you can have a flame, and why in some situations does the flame just blow out and you can't stabilize. All right? So what I want to do here is I first want to talk through a few introductory concepts, and then I'm going to talk in detail about flame stabilization and shear layers. And my guess is I've used up all my time, and I'm not going to have time to talk about flame stabilization by stagnation points. But we'll see how far we get. So let's start with some introductory concepts. So flame stabilization, in order to have a flame sit, at any real combustor, the flow velocity is much, much greater than your maximum flame I mean, otherwise, the power density of your combustor would be so low, it just wouldn't be practical. So your flow velocity is much, much higher. So in order to have a flame stabilize, you've got to have a point where the local flow speed and the local flame speed match. All right? So again, where the displacement speed, basically the flame speed, equals the flow velocity at some point. All right? Well, again, on average, this flow velocity is much, much greater than the flame speed. So typically, you'll find this inequality in low velocity regions, in low flow velocity regions. For example, in aerodynamically decelerator regions, VBB stands for Vortex Breakdown Bubble. Sorry for not writing that out. But think about this picture that I drew here. If you don't have flashback, you can actually have a stable flame sitting here. And as I told you, the flow is a stagnation point, has a low velocity region. So this is a potential flame stabilization point. And there are commercial designs out there which use exactly this principle to hang onto a flame. So that you can have aerodynamic deceleration. The other is a region of high shear, where basically in a boundary layer, a separating boundary layer, where the flow velocity goes from 0 to some core flow velocity. Well, in that transition region, is going to be a region where the flow velocity is quite low. And so ISL denotes inner shear layer, OSL denotes outer shear layer. And I'll draw you some pictures in a minute to show you. So I want to talk about flame stabilization of both of these. As I mentioned, I'm probably not going to be able to get to these, so I'm going to focus on why can a flame sit in shear layer in some cases, and why does it blow off in others. Okay, so let's go back to basically the classical treatment of premixed flame stabilization. So if you look in any textbook, you'll see pictures that look like this. And what I'm drawing here is these black lines labeled A, B, and C denote 3 different velocity profiles with 3 gradients. All right, so this would be a high gradient velocity profile, A. C would denote a low gradient velocity profile. This dashed line denotes the profile of the flame speed. And so what I'm drawing in here is you have some uniform flame speed in the core, and then it abruptly drops to 0 at the quenching distance. All right, so we know that in order to have a stable flame, well, if I have this configuration A, the flow speed is everywhere greater than the flame speed. This flame is going to be pushed downstream, right? Because the flow is going faster than the flame. It'll be pushed downstream. I'm not going to say yet whether it would blow off, but it will at least be pushed downstream. Configuration C, the flame speed is actually higher than the flow speed in some regions. So this is a flame that's going to actually propagate upstream, right? It'll flash back. Configuration B is a special case where the flame speed and the flow speed exactly match at one and only one location, right? And so this is a stable flame. The flame will hang on right there. And then what happens is the flow velocity is greater than the flame speed. That's OK. I'm going to have a stabilization point right here, and then the flame will just propagate away from this stabilization point at some angle given by sine theta is equal to S over U, which you can, in your classical combustion. OK? So if you look at this, you'd say, wow, stable flames should be really rare. Most flames should either flash back or blow off. Only one case can I get this to happen. It turns out, however, there are intrinsic self-stabilizing mechanisms. For example, if you have configuration A, the flame will be pushed downstream. Well, if the flame is pushed downstream, it's not going to be in contact with hot metal anymore. This quenching distance might go away, and then this velocity profile, this SD, this flame speed profile, won't stop here. It'll penetrate farther. All right. In the same way, if the flame starts to flash back, you might get more quenching, which would push this quenching distance farther out. So in reality, flames have self-stabilizing mechanisms, so there is a window where you can have a stable flame that doesn't flash back to blow off. But what you can have here, this is a plot from Lewis and von Elbe's textbook, equivalence ratio, flow velocity, and what you can, if the blow off is occurring in air, you have, if you have a flame into air, you have a flashback region here, you have a blow-off line here, and then this window in here is your operability window. This is where you can operate and have a stable flame. If you change your diluent, this curve changes to a curve that mirrors the flashback curve. Similarly, if you have a flame that's aerodynamically stabilized, oftentimes if the flame starts moving downstream, the flow velocity profiles will adjust accordingly so that you can have some range of flow velocities where you can actually have a stable flame. Okay, now what makes life really interesting is in that most realistic type geometries, particularly in swirl flows, and every commercial gas turbine out there today has swirl flows. So this is why I'm going to talk a lot about swirl flows. There's actually not one anchoring location, there's multiple anchoring locations. And so let's just talk about this geometry for a minute. It's not a universal geometry, but it's a pretty typical geometry where you would have a, let's go back to the same geometry. Usually what you have is a center body in the flow. So you have premixed reactants here. So this would be your mixing section, and this would be your combustor. So you got fuel and air being mixed in this region, and then this is a center body. And this would be your mixing nozzle, right, which we want to keep the flame out of for a flashback reason. And here's your combustor, and we want to keep the flame here. We don't want it to blow out. So the new element that I've added is the center body. The reason that people add these center bodies is that in swirl flows, it's really, really hard to design a swirl flow profile where the vortex breakdown bubble doesn't penetrate way up into the nozzle. It's really hard to make this core region not have a vortex breakdown. So the easiest thing is just stick a hunk of metal in there, and then you don't get vortex breakdown by definition. It's also nice for pilots or steam injection or other things like that. It's used as a fuel lens. But this is a pretty typical geometry. And so what you can see here is that you can actually have multiple places where the flame can stabilize. So look at that top left image. These are line of sight chemiluminescence images, but basically what's happening is the flame is sitting down here like this. All right, it looks like that. That's what you're seeing there in that top left image. So how is the flame able to hang on out in the middle of the flow? I have vortex breakdown. There's a stagnation point right out here somewhere. The flow is decelerated to 0 velocity, and the flame can hang on right there. All right? What happens, though, is as I increase flow velocity, I march from top left to top right to bottom left to bottom right. What happens is, above some critical equivalence ratio, I get a bifurcation. And if you're watching this flame and you're increasing the equivalence ratio ever so slightly, all of a sudden, bang, the flame pops back. It sits in this inner shear layer. All right? So remember I said there's two places the flame can stabilize. Either an aerodynamically decelerated region or the shear layer. So it sits in the shear layer. Now the flame spreads out like that. Right? Actually, then the flame will all of a sudden abruptly change shape here. That's due to a change in the vortex breakdown size. I won't get into that. What happens then, as you further increase the equivalence ratio, is all of a sudden, bang, the flame will all of a sudden wrap around and it'll catch in the outer shear layer. This is what I call the OSL. So now you have reactants, and this is this premixed flame that being turned to products as they propagate through the flame. So you have the flame, this annular type shape where the flame looks like this. And these discontinuities are very abrupt and they depend on lots of interesting stuff. And so the point I want to make here is blow-off is a very interesting problem. Flame stabilization, just figuring out where in the world the flame is going to sit, is also a really interesting fundamental problem. I just drew you, these are for this geometry, these are 4 possible flame shapes that you can have, depending upon where the flame is sitting. And so you can see that what the flame looks like, how the heat release is distributed, where, how long the flame is can be totally different from the exact same combustor. And these changes are discontinuous. So if you think about a lot of the very interesting combustor operability issues, durability issues, emissions issues, these are directly tied to which one of these flames you're going to have. For example, heat loadings to combustor hardware, which has an important influence on durability. You can imagine that this geometry, this geometry, this geometry would have much higher heat load in your nozzle section than this one. Right? This nozzle is totally out of space. Combustion instability boundaries. I'll get into this tomorrow, but I'll tell you now that the flame length, or the physical length of the flame, is fundamentally is a fundamental driver for where you do and don't have combustion instability. So if your flame is sitting in the inner and outer shear layer here, it can consume the fuel and basically half the flame length is just sitting in the inner shear layer. So you can get this very abrupt bifurcation where the flame length just goes pop, it changes by a factor of 2, and if that happens to move you into a region where you have instability, all of a sudden you'll be creeping along, making a small change, and all of a sudden, bang, the thing might start oscillating like crazy. By the way, this happens. There have been some commercial gas turbines that actually had to be derated. Which means they allowed the power to plug in. What would happen was the max power that they could get out of the system was about around 93% of the rated power. So, but what would happen is that, let me back up 1 minute. The boundaries between these, by the way, have hysteresis. So once the flame, if I increase my equivalence ratio, so all of a sudden it catches in the outer shear layer. Once it starts heating up that outer boundary layer, it can hang on. So there's hysteresis. So let me back up. So the the max power was 93%. Although they hit an instability boundary at 95%. The reason for that is that this would be a turbine, great big 250 megawatt gas turbine. They'd be creeping up in power, and all of a sudden 95% they would hit this enormous combustion stability. By the way, the example that I gave you in Chile about what happened was they would hit this enormous combustion stability, and their combustion chamber was actually lined with big ceramic tiles. And those combustion stabilities, before they could pull the instability back out of it, one of those tiles would go flying downstream. You had a 10-pound hunk of ceramic in your turbine. But what happened is you had this hysteresis. So once you hit it, all of a sudden, Tim Lieuwen's hypothesis is they had an abrupt bifurcation of flame shape. So all of a sudden, they're moving along, all of a sudden, pop, they hit this thing. So they'd say, oh, shoot, you back off your equivalence ratio, but you don't pop right back into it. There's this hysteresis zone. And so, very interesting things on combustion and stability limits. And then obviously, blow-off limits is effective. When the flame can't find any stabilization locations, that's ultimately blow-off. But the point I'm trying to make in this slide is blow-off is just one problem out of this more general issue of flame stabilization locations. Because what's the difference between this configuration and this configuration? The outer shear layer has blown off in this configuration. It's hanging on the inner shear layer here. Here, both the inner and outer shear layers are both blown off. Ultimate blow-off, there's nowhere that it can hang on. Okay, so let's talk about flame stabilization and shear layers. Well, shear layers are regions of very high shear, obviously. Very, very high flame stretch. How many of you are familiar with the concepts of flame stretch? Okay, that's kind of a bummer. My next 10 slides require some knowledge of flame stretch, but that's okay. We'll figure it out. If you take a flame, if you take a laminar flame in a uniform flow, it's got a flame temperature. It has a burning velocity. It turns out that as soon as you curve a flame, actually I talked about this before, you change burning velocity. All right. As soon as you make the approach flow velocity non-homogeneous, as soon as you start getting, for example, if any of you are familiar with stagnation flames, as soon as the flow in front of the flame becomes inhomogeneous, so this is a flame, and my flow velocity goes like this. That's going to change the flame speed. It's going to change the local flame temperature. And in fact, if you, what happens is what I referred to before as the Markstein number. The Markstein number is the sensitivity of the flame to curvature or flowing flame stretch. Turns out that if you that depending on the flame, depending on the reactance, depending on the stoichiometry, stretch will either have a favorable or an unfavorable impact. But all flames have the same thing in common. If you give too much stretch, they'll go out. They will extinguish. You can only have so much shear or so much curvature on a flame before it extinguishes. So, for example, in hydrogen flames, which have positive Markstein lengths, DNS simulations often show flames that look like this. Where this is reactance. So basically, this is the highly curved leading edge of the flame, except I had it backwards. This would be a lean propane flame. It would look like that. The flame, you can see accelerated burning right here. And the flame actually extinguishes on the tail end. It's just too curved. Anyway, so the flame will extinguish when the flame stretch rate exceeds what I'm going to call kappa extinction. Kappa extinction is the extinction stretch rate. All right? And you can compute it. You all can go in, take ChemCam, run some premixed post flame calculations from time to time. And so what this says is, though, is that even then, if you think about a velocity profile in your boundary layer, even if you have, let's just back up. Even if you have a location where the flame speed matches the flow speed, because of this velocity gradient, that flame is going to be stretched. And if that velocity gradient is too much, the flame will extinguish. All right. So this goes back to the point that the flame speed profile is a function of the flow that it's in. It's not something you can impose just because you know the reactance. Flame speed is stretch sensitive. So what I want to do is, well, let's just talk about this for a minute there. In a high-speed flow, although you can locally have a low velocity in your shear layer,
generally what happens is you start to get local flame extinction because your extinction stretch rate falls below the local flow stretch rate. So just to give you a number, what is the stretch rate that, what I want to talk about is what is the stretch rate that flames see. Just to give you a number, a 50 meter per second jet with a 1 millimeter shear layer thickness, this gives you a fluid mechanics strain rate, du by dx, of about 50,000 inverse seconds. Right? Just for your context, but I want to emphasize this is fluid mechanics strain rate. So if you think about your shear flow, your first graduate fluid mechanics class, we talk about fluid mechanics strain. That's what I'm calculating here. Now this number is much greater than typical extinction strain rates. Extinction strain rates for methane air and standard temperature and pressure is a couple hundred inverse seconds. This is really high. But this raises the question is, what is the relationship of flame stretch, which is this quantity that flames are sensitive to fluid mechanics strain in a boundary layer? That's what I want to walk through here, in a shear layer. So let's talk about where does flame stretch come from? Well, there's really, there's a couple sources. One is flame curvature, which I've mentioned. The other is if the flow or the flame is unsteady. And then the third is hydrodynamic strain. That's kind of what I was drawing here. When the flow is not 1D coming into the flame, but you start having inhomogeneities in your flow profile, that's flame strain. And again, I don't have time to get into the details, but the reason for this is that you start monkeying with the balance between the preheat zone and the reaction zone in a premix flame. As soon as you start having this, well, let me just draw a picture real quick. If you think about one-step asymptotics, you have a preheat zone here, and you have a reaction zone here. And the reaction zone, let me just finish drawing my picture here. The reaction zone pumps heat back into the preheat zone, and the preheat zone gives preheated stuff. All right, so this is just a one-step description. Well, as soon as you have this, what happens? The convective flux becomes misaligned with the diffusive flux. Right? So diffusion is normal to iso concentration or isotemperature gradients, right? So temperature is going to diffuse this way. Convection is fluid is being convected this way. And so what happens is that if everything is aligned, let me draw this picture where everything's aligned. I got a streamlines here, and I got diffusion here. This would be an unstretched flame. Everything's aligned. Well, the reaction zone loses heat. In fact, it gives all the heat back to the reaction zone, but that's okay. The reaction zone, the preheat zone, convects all that heat back into the flame. So you locally have heat transfer passing back and forth, but on a total energy point of view, the diffusion flux in one direction is balanced by the convection flux in the other direction. Well, what happens in this picture? You lose that balance. The flame starts giving off heat and it doesn't give it back, or the flame starts giving off radicals and they don't give it back, or the flame might get locally reactant radicals or heat that it didn't locally generate. That would be an accelerating effect. So that's why stretch is a problem. And hydrodynamic stretch is basically this configuration here. You have hydrodynamic stretch when your temperature gradients, your concentration gradients, which are normal to iso surfaces, aren't aligned with streamlines. Okay? And this is just a tensor formula telling you what I just said. All right? That flame stretch or flame strain, the words are used interchangeably, is given by this formula where you have this tensor velocity, u is the velocity, x is your component, and here's your Kronecker delta, and here Ni and Nj are your normals to the flame. So here's a 2D coordinate system. Here's your instantaneous flame. It's spreading at some angle of theta, normal direction, and then I can decompose that into an Nz and an Nx. So these would be the scalar components of the normal, which are given there. For reference, fluid mechanic strain is given by this tensor right here. And you can actually see some similarities. You see this dui by dxj term right there, but you can see the flame doesn't just care about fluid mechanics strain. It also cares about the orientation of the flame with respect to that strain. You see that Ni, Nj term. So what I want to do is I want to try to relate this to that in a shear layer. Okay, so what I'm going to do now is we'll just do some math. So if we assume that my approach flow is two-dimensional and incompressible, I can take that fluid mechanics stretch term and I can write it in this way. And what happens is immediately what falls out is the stretch that the flame sees has two contributors, what I'll call normal strain and shear strain. All right, so normal strain is if I take a fluid mechanic element
and it's incompressible. I squish it in one way, and it bulges out in the other direction. All right? Shear strain is when I take that fluid element and I rotate it, right? So, in other words, the normal strain says I take a fluid mechanic element that looks like this, and then I make it look like that. All right? Shear strain says I take this fluid mechanic element that looks like this, and I make it look like that. Right? So, you can see that I have this normal strain. Well, that contributes to flame stretch through these terms. I have shear strain that contributes to flame stretch through those terms. So I want to unpack these a little bit. Let's start by looking at shear strain. Well, fundamentally, sorry, I'm giving pause because some of this stuff I've assumed a lot more familiarity with flame stretch. So I'm going to just think about how I want to present this for a minute. Well, I guess you'll just take my word for it. I'll just tell you that fundamentally what causes, the reason we use the word flame stretch, if you think about a flame as a surface, if you think of it, if you're stretching it, the flow is, if it's pulling on it like a rubber band, that's positive stretch. If you're squishing it, it's negative stretch. So let's think about what happens to shear. So here I have a flame, it's stabilized in a shear layer, it's attached at this point, and I have this flow velocity profile. So clearly I got shearing fluid mechanic deformation. But what is it doing to the flame? Let's take these flow vectors and let's decompose them into their components, normal and tangential to the flame. So I've taken this vector, here it is, but I've decomposed it into a contribution normal and tangential to the flame. All right? Same for this one, normal, tangential, normal, tangential. So from a stretch point of view, what the flame cares about is how is this tangential component changing along the flame? What's happening? If the tangential component is accelerating, if the flame was a rubber band that was moving with the flow velocity, what would be happening? It would be getting stretched positively, right? Stretched positively. And so when a flame is sitting in a shear layer, it is getting positively stretched by shear, right? All right. Let's talk about the normal component. Now what I've done is I've assumed, generally in combustion chambers, the flow accelerates abruptly when it goes into the combustion chamber because there's a rapid expansion. So I'm going to assume that as the flow exits into my combustion chamber, it's decelerating. So I'm going to ignore the shear part for a minute, but I'm drawing my velocity vectors. I got high flow velocity here, and then it's decelerating as it's moving up. Okay? So this is causing fluid mechanic strain. The flow is the Lagrangian fluid mechanic volumes are changing their shape. So what's that doing to the flame? Again, let's decompose it into the normal and tangential components. And look what's happening to this tangential component as I move along the flame. It's decreasing. So what's that doing? The flame is getting compressed. It's getting compressed. All right? That's negative stretch. So what you can see is fluid mechanic deceleration leads to negative stretch. So actually, and by the way, the reason I'm talking about this is that any flame in a shear layer, like I said, you'll almost always have some flow deceleration. All right, so again, I have some math here, so let's take those same ideas and let's try to figure out approximate scalings for how fluid strain is related to flame stretch. So I'm going to skip over the details. I'll let you look at these. But what you can show is that the shearing component is related to the straining component. Excuse me, the flame stretch is related to flow strain by this formula. And this duz by dx denotes uz is the velocity in the axial component. X is the direction this way. So this is a shear term, right? It's how much is the axial velocity changing as I'm moving. And you can see that it's related through theta. Theta is the flame angle. All right, so this is a very important formula because it relates flow strain, flame stretch. And you can see that the important relator is theta. So you can see that actually, if theta is 0, if the flame is perfectly parallel to the flow, no stretch. The flame is totally unstretched. So unfortunately, this nice simplification, which we might want to invoke, is that the theta is pretty close to 0. It turns out that theta is really important. Let's look at the normal stretch. It looks like this. It's duz by dz. So it's the deceleration of the axial velocity in the axial direction. It turns out that the theta here, we can basically assume it's 0. It doesn't really change the answer. So there's these two terms. The shear term is multiplied by theta. The axial deceleration term is just by itself. So what this tells you actually is this says that flame stretch due to normal strain is exactly equal to the normal fluid mechanic strain. It says that flame stretch due to shear is equal to flame flow strain due to shear times theta. So let's think about scaling these for a minute now. Here, let's look at shear strain. So flame stretch due to shear is equal to theta times du by dx. Well, what's theta? Let's think about what theta is. If the flow velocity is high relative to the flame speed, which it usually is, a good formula, I can replace sine theta by theta. All right? So sine theta is equal to flame speed over u. Well, it's basically theta. And so theta will approximately equal the flame speed over the flow velocity. All right? And so as the flow velocity becomes very large relative to the flame speed, theta approaches 0. And so what that says is if we take that formula, the flame stretch rate scales as flame speed over u times du by dx. So how would we scale this? Well, in terms of scaling, the u should cancel. The d by dx is basically going to be a characteristic boundary layer thickness. So this term right here, what this tells you is that the flame stretch rate due to shear scales as flame speed divided by shear layer thickness. All right? So flame speed divided by shear layer thickness. So what does it tell you? It tells you that the characteristic velocity scale for shear strain is not the flow velocity, but the flame speed. Another question you might ask is, well, where is the flow velocity in here? There's no flow velocity. So what this is telling you is that if somehow you can fix your shear layer thickness, delta, doubling, tripling, quadrupling your flow velocity has no impact whatsoever on flame stretch. And why is that? Well, it's because of the canceling effect of theta and du by dx. So if you double your flow velocity, you double your fluid mechanics strain. All right? But you half the flame angle. Theta goes down. The two exactly cancel. So key point here is that fluid mechanics stretch, fluid mechanics strain are not the same thing, and there can be some very interesting relationships between them. So does this, but you might ask, well, it's a pretty typical observation that as I increase flow velocity, flames blow off. So, and this is saying that it's independent of velocity. Well, in fact, there is a velocity dependence buried in here. Boundary layer thicknesses, for example, a laminar boundary layer thickness is 1 on square root of u. So there is a velocity sensitivity, but it's a square root of velocity sensitivity. OK, let's look at stretch induced by normal strain. If you scale that term, what that says is that the normal strain contribution scales as u divided some characteristic length, L. And so this says that the flame stretch and fluid mechanics strain are 1-to-1 related. All right, so let me ask the next question, which is what is the total flame stretch? I showed you that flame stretch, there's two contributors, which add. Which one's dominant? So what I've taken now is I've taken those two approximate expressions and I've substituted them in. Here's the normal component, here's the shear component. And remember I said there was something that I said before, which I said this term was positive and this term was negative. It's always life is always more interesting when you're adding two terms with opposite signs, right? Because little changes can have really big effects. Right? If I take 1,000 plus negative 1,001, I get negative 1, right? If I take 1,000 plus negative 1,002, which is a 0.1% change, I get negative 2. So my answer just changed by 100% because of a 0.1% change in flow velocity. So for this reason, I personally despair from ever being able to scale stretch rates and shear layers because of this super duper sensitivity. So you have this opposite sign, and so you start having to ask yourself which term dominates. And I want to show you why this is a very interesting problem. In a shear layer, the shear term, which is du by dz, the gradient of velocity in the flow direction, in the radial direction, is going to be much, much. I had this backwards. Oh, excuse me. This is what I would have already neglected this term. Let me look at this term right here. The shearing term, dux by dz, is going to be much, much bigger than duz by dx. No question. All right. You have this huge shear. The flow is decelerating, but nothing compared to the thickness of the shear layer. The problem is this great big shear term is being multiplied by a small flame angle term in high velocity flows. So here you have a term, which is one sign, and I'm trying to compare it to a term with another sign where I'm multiplying a big number by a small number. So which term wins? It's not obvious which term wins. I'll just tell you, we've gone in and we've tried to measure this. And this term, this is a little bit of a mess, but basically this term here is the flow deceleration term. This is the normal strain. This is the shear strain. And I'm plotting the distribution as a function of downstream distance. I have a flame stabilized in a shear layer. And I'm trying to figure out who's dominating, shear strain or normal strain. You can see this term is negative, this term is positive. And I have a bunch of terms which are small, which I should have gotten rid of. But what you're interested in is this. This is the resultant flame stretch. And by the way, this value is negative 0.2. Here's positive 0.2. Dimensionless units. The dimensionless unit of 1 is 4,000 inverse seconds. So these are about 800. So the maximum negative stretch rate is about 800 inverse seconds. But you can see I have two terms, comparable magnitudes but opposite sign. You can see actually the near field of the flame is actually negatively stretched. So what this tells you is that in this swirl flame where we took this measurement, although the flame is sitting in this shear layer, the strongly positively stretching shear layer, the flame is actually being negatively stretched right at the attachment point. Farther downstream, it reverts to a positive stretch. This is a really interesting problem. Just because of its pure sensitivity, you're taking two terms, opposite sign, one of the terms, you're multiplying a big number by a small number, all kinds of crazy stuff can happen. Lots of sensitivity to stuff. Scaling flame stretch rates in shear layers is a really interesting problem. Okay, does anyone have any questions about that? All right, I want to add another layer to this flame stabilization issue, which is piloting or flow recirculation effects. All right, oftentimes to stabilize high velocity flames and high velocity flows, you either force some flow recirculation or you put an external pilot in. All right, so for example, this is what's called a dump combustor. You have this, and you force flow separation. Here's your flame, and basically once you initiate combustion, you have hot products continuously being recirculated, and those products are continuously reigniting your reactants here. Same thing happens here. Here's a bluff body flame like would be used in an afterburn. Similar deal. You force flow separation, and by flow separation, you have stagnation pressure loss. You say, you know, I got to stabilize my flame, so I'm going to lose a little stagnation pressure. Or this is a swirl flame, and here I have this vortex breakdown bubble, which causes some flow recirculation, and actually this rapid expansion gives me flow recirculation. So oftentimes this is what's used to stabilize the flame. And this is interesting because when you start piloting flames, or when you have very high preheat, this whole phenomenon of flame extinction kind of goes away. All right? And what I'm going to talk to you about is blow-off doesn't become an event like it does in a simple Bunsen flame where you have the flow, you have a flame, you increase the velocity, and bang, flame's gone. Blow-off becomes a process. And in order to illustrate that, what I have here are some calculations. Basically, why do flames extinguish? Think back to your combustion theory class. Extinction is fundamentally a fact that you have high activation energy. High activation energy gives you this S-curve. You guys remember the S-curve? S-curves mean you have distinct extinction ignition events. Right? So actually, I think you probably in your notes, if I remember from your combustion theory, for those of you who took it, if this is like a Domkohler number, you get a phenomenon that look like this, where this is combustion temperature. And you basically have a no reaction branch. You have a complete reaction branch. You have this hysteresis regime. This is extinction. This is ignition. And basically what's happening is we're stretching. When you stretch a flame, you're basically moving in this direction. Too much stretch, no flame. All right? Well, this means this occurs. You get S-curves because of high activation energy. Right? What's activation energy? It's E sub A over RT. And again, this is single-step kinetics. Real flames don't have single-step kinetics, but we'll just run with this for a minute. Well, there's two ways that you can not have. As soon as you lose high activation energy, the S-curve goes away, right? So if the high activation energy is not high, you'll get something that looks more like that. Now, when the S-curve gets stretched out, you have no extinction, no ignition. It just says, well, as I decrease my Domkohler number, I just get less and less reaction. It's basically a chemical reactor. I give my combustion a little more time, I get a little more product. I don't have these abrupt switching on, switching off events, which we're also familiar with, right? And by the way, we're all happy about this, right? I mean, at my home in Atlanta, I have a can of gasoline in the garage, and I feel good about it. I'm not nervous about it, being over here. And I feel good about it because I know I'm on the lower branch, and unless some neighborhood kid walks over with a match and kicks me up to here, my garage is going to be fine, right? If I didn't have high activation energy, if the curve for the gas in my garage looked like this, I wouldn't put it in my garage, right? Because what would happen? You'd get a little reaction, which is raise the temperature, a little more reaction, raise the temperature, and at some point it would go. But anyway. So we're oftentimes used to thinking about activation energy, but really dimensionless activation energy is what matters, this ratio. So as you increase preheat temperature, you can also lose your S-curve. So what happens when you have all this recirculation is the flame has no S-curve at the stabilization point. It doesn't extinguish. Its combustion efficiency drops. And just to illustrate this point, here I have a couple calculations. Whoops. These are, what I'm doing is I'm stagnating reactants against hot products. All right? And the temperature here denotes the temperature of the hot products. Okay, so reactants against hot products. It's a rough model for a flame stabilized in a shear layer with product recirculation. And at 1350 K, and here I'm increasing the flame strain rate. Okay, and as I talked about, as you increase flame strain rate, this is the consumption speed. This is the amount, the average burning, the average consumption of reactants. What happens is it drops, and then there's this critical point when bang, I drop to zero. So the flame very abruptly extinguishes. And this dashed line just denotes the unstable lower branch. But what happens is that about 1400 K, you lose this tangency point. At 1450 K, you basically lose your S-curve completely. So what that means is I can stretch the flame more and more and more and more, and it just kind of hangs on. I just get less and less combustion. I'm also plotting the displacement speed here. How many of you are familiar with the difference between consumption and displacement speed? So never mind. Just worry about the consumption speed curve. So that happens. And so what that means is that actually, as long as you got product recirculating, that flame's just not going to extinguish in the shear layer. And so what happens is that when you have recirculation stabilized flames, again, as I said, blow-off becomes a process. It's not an event. Okay? So let me explain what I mean by this. What I have here are a bunch of images of a bluff body flame, stabilized flame where I'm close to blow-off, but the flame is not blown off yet. In fact, the flame will look like this perpetually. All right, and what you're basically looking at are different realizations of the flame. And you see these holes in the flame that are opening up, they're convecting downstream. The flame will sit like this forever. All right, what's happening is that locally, the flow velocity is very high, the local stretch rate is very high, and the flame is locally extinguishing. But it's never extinguishing in that critical stabilization region because it's supported by recirculation. It extinguishes a little bit farther downstream. Notice where these holes are always opening up. And so what you have here is you have these stages of blow-off. Flame is continuous, but you get these local extinction events where locally the space-time flame stretch starts to drop below the extinction stretch rate, and the flame locally opens up a hole. Well, now as I keep increasing the flow velocity, a larger and larger fraction of the flame starts being extinguished. So in other words, here, I got a couple holes in the flame, but no big deal. If I keep dropping the fuel-air ratio, what will happen is more and more of the flame downstream will be extinguished, but it will still hang on in the near field because as long as it's being piloted, it can't go out. The flame does not extinguish. But what happens is something that's not extremely well understood is this stage 2 of blow-off. Okay, don't take me wrong. This flame will eventually blow off. But what happens is blow-off is preceded by this whole range of fuel-air ratios where there's just kind of very crazy combustion, where the flame's got lots of holes and all kinds of crazy stuff's happening. And what usually seems to happen is that as you start to approach blow-off, you start to get some wholesale changes in the fluid mechanics, the hydrodynamic stability of the flow. And all of a sudden, for some reason, we don't really understand what's happening. As you move from stage 2, all of a sudden, bang, the flame blows off. But this relationship between stage 2 and stage 3 is still a very active subject of research. So a very common approach to model blow-off is what I'll just call a Dom-Kohler number approach, where you basically take a characteristic chemical time, characteristic flow time, or a characteristic flame stretch rate and extinction stretch rate, and you compare them. All right? What those approaches are doing is those really are not approaches for capturing blow-off. Those are approaches for capturing stage 1. So what those approaches are doing is they're saying, when am I going to start to get extinction on the flame? But as you can see, that when you have product recirculation, extinction and blow-off are different things. And so really what the community is doing to understand blow-off is really to try to understand extinction. The reason they seem to work reasonably well is that the extinction event and the blow-off event are related, and they occur in certain regions. But this is a really interesting question. I think we have a pretty good understanding of the stage 1 of blow-off, but in real flows, understanding the stage 2 and why flames, what finally causes that flame to let go is a really interesting problem. Here I actually have some visualizations of the same thing in a bluff body. This is chemiluminescence. You can see that the flame, you can see extinction, but the flame is always hanging on right in the wake of that bluff body because it's getting piloted. It won't extinguish. But eventually what's going to happen is some kind of fluid mechanic event will happen where all of a sudden you don't have hot products in here. Maybe it'll get moved over, it'll get pushed downstream, and you only have cold reactants, and that's when the flame lets go. OK, I have 7 minutes. OK. You know what? I have a feeling. Let's just stop here with this stuff, and maybe I'll take some questions because I did go through that material rather quickly, and I'll just let you look at the flame stabilization by stagnation points on your own. Does anyone have any questions? Yes, sir.
Could you comment on the low swirl burners which are in the block and the prospect of controlling them, even technically?
Yeah. So you're asking me a question about this topic. I'm not going to talk about flame stabilization by by aerodynamic stabilization. So the low swirl burner, the idea there is you run at a swirl number below where'd it go? Oh, it was in the previous. OK. Anyway, in the previous, if you remember, I drew that bifurcation diagram of a swirl flow where I said you always get breakdown. You're in the hysteresis region, and you never get breakdown. So a low swirl burner operates in the region where you're never breaking down. However, one thing about swirl flows is they have very rapid divergence. So if I take a flow with a swirl that's below the critical level, the flow is going to very rapidly diverge. Because it's swirling, it just gets spun out by pure centrifugal force. And so you get a lot of deceleration. And what will happen is the flame can just find a spot where the flame speed matches the flow speed. It's actually stable. If the flow velocity drops, the flame can find a spot closer. If the flow velocity increases, this will just get pushed downstream. And so there's these stabilizing mechanisms. And so it actually turns out to be a really slick scientific device for making a flame just sit there in one reasonably well-defined region in space in a flow without shear. It's also been proposed as an idea for a lower pressure drop device for stabilizing flames. So, you know, it's an interesting idea. I guess what's the specific question about? I was just explaining the rest of the class, I guess, but I don't.
Well, I was just asking whether you think it's going to be possible to control that. Because you can fluctuate.
That's right. So I will tell you that most gas turbine companies I've talked with have a hardwired nervousness about flames stabilized out in free space. They want a piece of metal for it to hang on to. The question is whether you can design this device such that it has enough turndown and range that stable range exists. And frankly, I mean, that's so geometry specific, I wouldn't even want to, and fuel specific, I wouldn't even want to make a general conclusion about it. But I mean, there certainly is an operational window where you can find where you can have a stable flame. One of the interesting things about a low swirl burner is you don't have vortex breakdown. As soon as you have vortex breakdown, you actually lose some pressure. You lose stagnation pressure. And again, if you think about your cycles class, loss in stagnation pressure across the combustor does have a direct hit on cycle efficiency. So it's an interesting way of possibly stabilizing a flame with a lower stagnation pressure drop across the combustor. And also, you know, Robert Chang, our friend Robert, would also point out that because if there's no flow recirculation, There's no Zeldovich. Remember, Zeldovich Knox is proportional to temperature times resonance time. So you don't have this piloted region, which is just spinning around making Knox proportional to time.
But you may run into flashback at one point.
Oh, sure. But I mean, any burner will run into flashback, I guess. But the beauty of this one is, that whole combustion-induced vortex breakdown mechanism just totally goes away. But yeah, there will be a velocity range where flow could flash back. But if you design it below criticality, then at least you know the flow won't break down in the nozzle. Yes?
Could you just comment how much shape the black body used in the swirler affects stability? Are you aware of that?
Oh, yeah, it has a huge effect. Huge, huge effect. So you're saying that...
Because most of the swirlers that I have seen, the black body doesn't look like this. It looks like
it looks like what?
The black body doesn't look square.
It looks like that?
Yeah.
Yeah, it totally depends. If you look at, for example, GE's Swazzle designs, they all look like what I drew. If you look at... the problem with that design is, the bluff body that I drew, you get a region of flow recirculation. Behind it, you lose more stagnation pressure. The idea with this device is that you could possibly not have, you wouldn't have this strong wake. The problem is that for example, like a GE, like an LM6000 might look something more like this, or even a Siemens 501F would look more like this, where you have a much more shallow profile. And frankly, they're just, you're having, the only question here is you have to design the aerodynamics such that you don't get flow separations. Really, the big challenge is as soon as you make your center body narrow diameter, it's really tricky to not make the boundary layers separate. Because what's happening, you have, because of this strong deceleration of the flow, swirl flows impose a very strong adverse pressure gradient on the boundary layer. And so that inner boundary layer really, really wants to separate. And so that's why you'll see most designs have a center body in the swirler. Only Alstom is one I'm aware of that really doesn't. Just because of the difficulty in not, and you can do it, but it just takes a lot of careful aerodynamic design to not make boundary layer separation right there. Because again, you're screaming through here with some nozzle velocity, and the flow velocity goes to 0 at vortex breakdown. It takes a strong adverse pressure gradient. That strong adverse pressure gradient separates your boundary layer. Does anyone else have a question? I'm sorry.
Then you have to balance it probably with the expansion of force, the step there.
Yep. Yep. Absolutely. Yeah. So there's lots of very interesting fluid mechanic questions associated with developing a low NOx combustor. Anyone else have a question? All right, it's lunchtime, and I guess I'll see you all tomorrow. Thank you.